We should also be able to do hypothesis tests in this setting of a single proportion. And here I give you this, maybe by now somewhat boring slide, which is a copy of the slide I always bring when I mention hypothesis test in the lecture. That is just remembering to us what is a hypothesis test, sort of procedural wise. Well, we need to formulate the hypothesis to choose the significance level, or it is given to us by the circumstances. We should calculate, using the data, some kind of test statistic that measures sort of the difference between the data and the hypothesis, or the difference between the data and the claim, right? And then we either use a critical value approach, or we use a p-value approach to finish the story to find out, do we reject or do we accept the hypothesis? Here is a slide almost equal also to what we've seen previously in the course, but with something else still in it. Now the hypotheses are expressed in terms of the p. Here there could be, I mean, some people, if you were not confused at this point in the course, you may start to get confused. Because now, when we're going to do a hypothesis test now in a while, I talked about a p-value. A p-value, this is the name for the probability we may find as the end result of a hypothesis test, the probability measuring the oddness of the data, you could say, or the extremeness of the data. And today we are doing statistics and hypothesis tests about something that is also a p. That is also, you could maybe force yourself to think of it as a proportion, but it's clear that a proportion can also be seen as a probability, which it is. I mean, it is the underlying probability if you randomly select people that they are of this particular kind. That is the p. So the p that the thing we're interested in today is itself a p. But it's a p like a mu that we looked at a few weeks ago. And then we use then a new p-value comes up to say something about the conclusion about the p. So we use the word p. I mean, the letter p comes up many times during a day, so you shouldn't be scared about that it comes up more than once in your life. But then again, here, of course, it comes up sort of meaning a probability, but in two different ways. Maybe I confused you there. That's always the balance here. Maybe I should just not talk about it. Here is the test statistic that we will use in such a case. It's still based on a certain assumption of not having too small samples, like the confidence intervals that I just showed you. Let's look at this test statistic. We take the observed data, the number of people voting for Obama. Let's say a usual test for, if it's this Obama-Romney thing, would be to maybe test, that could be a common test to actually do. Could we assume a 50-50, or is it not 50-50? I mean, or is it, do we have a result somehow, or is it really 50-50? That is often a situation that you want to go for. Is there really a 50-50 or not a 50-50 situation? It's not always the relevant hypothesis, but it could be. What you want to do is take the number of people voting, or I should say, claiming that they're going to vote for Obama. I'm going to compare them with what we're going to call later also as the expected value. If I ask 1,000 people of how many are you going to vote for, sorry, who are you going to vote for? Then if I hypothesize, and that's what I'm going to check now, that it's a 50-50 thing, I will expect that n times 0.5, that is 500 out of the 1,000 will say that they vote for Obama. That is the expected value. I compare then, if I see 550, I compare the 550 with the half of the sample size, that is the expected value, n times p naught. I need to realize the sampling uncertainty of such a difference. What we say if I do this again tomorrow and tomorrow, how will such a fraction, such a proportion change from time to time? Well, that is the binomial standard deviation I have down here. Can you see that? NP, 1 minus p, square root of that. That is the, you could call it, this is the binomial, we could call it, if we should give it a name, the binomial standard deviation. So we divide by the binomial standard deviation. Then the theory tells us that if the hypothesis is true, that is, if P0, P0 is the right thing, is the right level of this population, then this test statistic, that's why we call it a Z, is because we can use the standard normal distribution to find out whether we have something off the null hypothesis or not. The sampling variability of this thing from sample to sample is a standard normal. That's the theoretical result that we can rely our intelligent decision on when we are doing the hypothesis test. So we evaluate what is going on using the standard normal. Let's try it. Then we have, this is a typical table. Today I'm not going to dwell on it. It's the usual thing. If the test statistic is too far out, either to one or the other direction, we reject. If it's not too far away, we don't reject. Right. That's what this table says in all situations. Which hypothesis test should we test now? Let's see. Let's go back to see. I didn't necessarily decide before I came here which one. We have a number of different cases that we were looking at. Let me see. Bugger. You don't give me very funny data to play with here. Which one should we take? Let's do a bit of cheating now to make it a bit more interesting. Just a slightly more interesting. It's not cheating. Now I think about it, it's doing the proper thing. It's correcting an error I did previously, right? Let's doing the female engineering students. Female engineering. It's difficult. Engineering. I think this is the way to spell the thing we do here at our university, isn't it? Students, not female engineering, what the heck that should be. Female engineering students. I saw 25 female engineering students out of a sample of, I think I didn't count correctly. You were actually 75 people in here. It couldn't be that you were only 50 people showing up at my lecture. So I'm sure it's 75 people. Sorry to you out there listening in different ways. Since I don't see you in your faces, it's difficult for me to poll you and talk about you. I know you're there. So anyway, I have 75 people in the room here. So the p-hat would be 1/3. That is 0.33. Let's try to test the hypothesis whether we have a 50-50 situation of female-male engineering students, assuming that my sample is okay, which, of course, as we discussed before, is obviously not okay. This is not a random sample. So this is really a convenient sample of the very convenient and questionable types. Anyway, let's assume that we're doing okay. Let's also assume that we know nothing about what we would expect or like to prove. We just want to check whether it's 50-50 or not. How should we do the hypothesis test? We should take the observed number of female engineering students in my sample. I should take the expected number. What is the expected number? That is the half of 75, right? Since P0 is 1/2 now, this is what we're testing. If I look at the formula from the slide from before, I should take, there should be 37.5. It couldn't, but there should be. That's the ideal number, 37.5 number of female students in this sample. If it should fit, if it should match the hypothesis exactly, then I should divide by what? If I don't remember, I have a look. Should divide by n. That's 75. And then P0, that was 1/3. 1 minus 1/3. And then I do this computation. Sorry. It was the P naught, of course, not the observed. Thank you. Like that. Let's see. What was that? Let's see. 25 minus 37.5 divided by square root of n times 0.5 times 0.5, 1/2, 1 minus 1/2, right? That is the set. What is set, the value? It's minus 2.89. Minus 2.89. Let's find the p-value of this hypothesis test, right? What is the p-value of such a hypothesis test? We take the standard normal. Here is 2.89. Here is plus 2.89. The p-value is the sum of these two percentages, right? This is the p-value. The chance of going beyond 2.89, be it in one or the other tail. That is the p-value, to be as different from the hypothesis as our data, or even more different. That is, how likely or unlikely, you may say, is 2.89? How is that likely or an unlikely deviation from the center of this distribution? The distribution shows what is a fair expectation that can happen alone due to chance. Is 2.89 fair or unfair, or likely or unlikely? We need to find this probability to say, is it extreme or is it not extreme? Let's try to find it. We should find the probability of being to the left of this set. And then I should also have the probability of being to the right of 2.89. And that is the same thing, so I could just multiply by 2. And the p-value becomes 0.004. Let's just say that, 0.004. Have we, given these data, have we then proven that the proportion of female engineering students is not equal to 1/2, or have we not? How many think we have proven that it's not half? Given, assuming that my sampling and I didn't cheat and all that, just assuming that it was okay, everything with the data sampling and with the data, should we reject, have we proven it to be different from 1/2? Yes. God damn it, yes. The answer is yes. I'm not going to ask if anyone thinks differently. We have rejected because it is unlikely, that's what we have found, 0.004 is small, because 0.004 is less than the nominal 5%, if that's the one I use. Maybe I didn't say that, but if I don't say anything, I use 5%. Like R, like any other statistical program. This is hypothesis testing for a proportion. Now we really need a good 15 minutes break.